The wedge and dash diagram for a trigonal bipyramidal structure is a little bit more tricky to draw. Typically, it helps if you draw the equatorial, flat, planar, triangular structure first, and then you simply add the vertical domains. And some terminology associated with these trigonal bipyramidal structures are axial and equatorial. So the equatorial positions are those arranged triangularly around the center that are in the same plane, and the axial domains are the up and down, the vertically arranged domains. The final electron domain geometry that we'll talk about is the one that has 6 domains arranged around a central atom. And 6 domains can be arranged around a central atom very symmetrically, with each lobe lying along one of the standard Cartesian axes. And all the angles are going to be 90 degrees. Each domain will be 90 degrees apart from another domain. And this electron domain geometry is known as octahedral. The prefix oct means 8, but there are only 6 domains. So the oct in octahedral comes from the fact that if you made this into a 3-dimensional structure, it would have 8 faces, or 8 sides. So typically the way you draw the wedge and dash diagram for an octahedral is to draw the 4 domains that make up the equatorial structure that are all in one plane, and then you draw the 2 vertical domains. And these are the baseline structures that we'll be working with. Now sometimes you have a mix of bonding and non-bonding domains in a single molecule. And we can describe those situations using something known as a molecular geometry. So the general baseline shape starts with the number of electron domains and the electron domain geometry. But when we talk about molecular shapes normally, what we care about is the position and angles of the bonded atoms and not the lone pairs. So we'll look at molecular geometry in comparison to the electron domain geometries. So we just saw that 2 domains gives you an electron domain geometry of linear. And the molecular geometry, the only molecular geometry that you can get with 2 domains, is also going to be linear. It doesn't matter whether these domains are bonding domains or non-bonding domains. It doesn't matter which ones are lone pairs and which ones are bonds. The only way to arrange 2 things around a central point and get them far apart is to make them linear. When you move on to 3 domains, you end up with an electron domain geometry of trigonal planar. And now we've got a situation where you can have different molecular geometries depending on the number of lone pairs. If you have 3 bonding domains and 0 non-bonding domains, that is 3 bonds and 0 lone pairs, you end up with a trigonal planar shape. This is exactly the same as the electron domain geometry. Nothing has changed. But if you replace one of those bonding domains with a lone pair, you end up with the second situation. Now you've got 2 bonding domains arranged around a central atom, and you have a lone pair as well. And in this situation, you have what is known as a bent molecule, because we only care about the position and angles of the bonded atoms. So a bent molecule would be something like the NO2- ion. The nitrogen is the atom in the center. It's your central atom. It has 3 domains arranged around it. It has a single bond, a double bond, and a lone pair. Each of these represents a single domain, and one of them is a lone pair, so a non-bonding domain, and the other 2 domains are bonds, so bonding domains. So you end up with a bent structure. When you move to 4 electron domains, you have a tetrahedral electron domain geometry. And you can have, again, a number of different molecular geometries. If you have 4 bonds and 0 non-bonding pairs, 0 lone pairs, you end up with a molecular geometry that's exactly the same as the electron domain geometry, tetrahedral. And this would be something like methane, CH4. If you start replacing bonds with lone pairs, you get a series of additional molecular geometries. If you have 3 bonds and 1 lone pair, you end up with something that is trigonal pyramidal. It still has 4 domains, so it has a roughly tetrahedral shape, but one of those bonds has been replaced with a lone pair. And now if you only look at the bonds, it looks like you have a triangular-based pyramid, and we call that trigonal pyramidal. And that would be something like ammonia, NH3. And if you have 2 bonds and 2 lone pairs, again, you have a roughly tetrahedral shape, but we only look at the bonds, and the shape of the bonds is very, very similar to that bent structure we saw earlier. And in fact, we call it bent. And this would be something like water, H2O. Water has 2 bonds and 2 lone pairs centered around that central atom, the oxygen. So it's tetrahedral electron domain geometry, but 2 of the domains are lone pairs, so it's a bent molecular geometry. We can move on and look at situations with 5 domains and 6 domains. And now we can do something similar. With our 5 electron domains, we have an electron domain geometry of trigonal bipyramidal. And this has a number of different molecular geometries. When you replace one of the bonds with a lone pair, you end up with something known as a seesaw shape. And this is because it looks like a seesaw or teeter-totter. Sometimes it helps to draw it at a different angle. You can imagine the solid lines pivoting around the dashed and the wedged lines, just like a teeter-totter. And an example of something like this would be SF4. And I've omitted the lone pairs on the fluorine atoms. If you go to 3 bonds and 2 domains, you end up with a structure that is T-shaped, very imaginative, and that would be something like ClF3. And then finally, if you go to 2 bonds and 3 lone pairs, you end up with a linear structure, because again, we only care about the bonds, not about the lone pairs. With 6 electron domains, you can have the following molecular geometries.